Okay, let me explain the solution here. So enemies planted landmines in the country zone at a rate inversely proportional to the square of number of mines planted. It takes them 2 months to plant a total of 2,000 mines. So first, we consider this part of the question first. So we are asked to find the total number of mines planted by the enemies just before the war ended. Okay, and planted. Okay, so the answer should be, okay, so let y be the number of mines planted since the start of the war. So when t equals to 2, that means it's 2 months, there are 2,000 mines planted. When t equals to 0, of course, the war haven't started, and so the mine, there's no mine, so y equals to 0. So the rate of planting the mines is dy of dt, which is equals to k over y square, meaning inversely proportional to the square of the number of mines planted, where y is the square of the y is the number of mines planted and y square is the square of the number of mines planted. So when we integrate this, so y square will move over to the other side and k here. So when we integrate this will become y cubed over 3 on the left hand side, and right hand side become kt plus c, where c is just an arbitrary constant. So from here we make use of the earlier part of this information given. When t equals to 0, when t equals 0, my y is 0, so 0 plus c, so 0 equals 0 plus c, so therefore c equals to 0. C equals to 0, and another thing is that when t equals to 2, y equals to 2,000, so I just substitute 2,000 here into this equation. So 2,000 cubed over 3 equals to, time is t equals to 2, right? So 2k plus 0 from the earlier part, we know that c equals to 0. So k equals to 3, so divided by 2 on both sides, so 3 becomes 6 and 2 disappears. So then we have 2,000 cubed over 6. So we sub this information back into the original equation again. Then we get y cubed over 3 equals to 2,000 cubed over 6 multiplied by 16, because I want to know when the war ended, which is 16 months later, what is the number of mines planted. So I substitute 16 into the t, and the k is just what we found earlier, c is equals to 0. So when 3, okay, so I multiply 3 on both sides, I will get 6 will become 2, right? 16 divided by 2 will become 8, right? 8 is just 2 cubed. So when I cube root both sides, I get my y become 2,000 times 2, so equals to 4,000. So 4,000 should be the answer to my 8 part 1, because that is the total number of mines planted by the enemies just before the war ended. But here later, and half the total mines planted had claimed casualties. When the mine claimed casualties, it is removed, so-called, right? Because it exploded, so there's no more mine remaining. So half of the mines had been cleared as they claimed casualty. So the number of mines remaining at the end of the war is equals to 2,000, right? Okay, so let x be the number of remaining mines planted by the enemies at time t. Okay, so my x when time t equals to 0 is 2,000, because half of the mines that were planted have already been cleared. So at the same time, so let's say Zhou then employed demining workers to clear the remaining mines at a removal rate that is inversely proportional to the number of mines remaining. So x is the number of mines remaining, and dx dt is just the rate of change of number of mines remaining. So when we say, okay, inversely, the removal rate is inversely proportional to the number of mines remaining, so minus k over x, right? Inversely, because it's inversely proportional, right? So then and at the same time, there's a constant casualty rate of a quarter of the number of mines remaining, so minus 1/4 x, right? Where x is the number of mines remaining. So then when I combine the denominator, I multiply I factorize out the negative sign and multiply 4 to this, so 4k, and multiply x to this, so it's x multiplied by x is just x squared over the denominator will combine become 4x. So then when I multiply over this to the other side, so it become 4x over 4k plus x squared dx. So on this side you can minus integrate 1 of dt. Then when you integrate this, we get t plus c, where c1 is a constant, and here I just factorize out the 2, so I have 2x inside, right? 2x because I want the numerator to be the derivative of the denominator, so I can apply this technique of integration. Let's say when the numerator is the derivative of the denominator, we can just, after integrate, is just ln the denominator, okay, equals to minus t plus c2. Okay, then the next step will be just removing these 2 over to the other side and have minus t plus c2 over 2, where c2 is another arbitrary constant, right? So then 4k plus x squared. So then when I move the exponential over to this side, okay, then so then 4k plus x squared. So ln, the inverse of ln is just the exponential, ln is just the log base e. Okay, so then when I divide 4 by divide everything by 4k becomes k, x squared becomes 1/4 x squared, and this part becomes 1/4 of what we have found earlier. So then when using the exponential rule, we know that e to the power of minus t over 2 plus c2 over 2 is just e to the power of minus t over 2 multiplied to e to the power of c2 over 2. So then here, since e to the power of c2 over 2, c2 is a constant, when you divide by 2 it's still a constant, when it's exponential of the constant is still a constant, and divide by 4 is still a constant. So therefore we just let all this be the constant a, which we'll be able to find later. So exponential minus t to the power of 2. So then it is what they asked us to show is 1/4 x squared plus k equals to a e minus t over 2, e to the power minus t over 2. So then from here, the contractor of the D mining company claimed that he will need 2 months to clear half the mines. So to clear half the mines, he need 2 months. That means when t equals to 2, the mines will be half of what was initially there, which is when time equals to 0. And we know that the amount of mines remaining at the end of the world was 2000, so half times 2000, so that means in 2 months the normal amount of mines remaining would be just 1000, right? So then next, we also know that when the number of mines remaining at the end of the world, when small t equals to 0 equals to 2000. So in case you are confused just now, it was big T representing the time after the war started, right? Now small t is representing the time after the war ended. Note the difference, started and ended, so we are considering different things. So now then, when we look at the equation that we have here, okay, we just substitute what the information we have to find the constants k and a. So firstly, I substitute 2000. Why do I substitute 2000? This, and substitute when t equals to 0, and substitute t equals to 0 and x equals to 2000 into this equation. So 1/4 2000 square plus k equals to a e to the power of minus 0 over 2 is still 0. So we have a equals to e to the power of 0 is 1. So a equals to 2000 square is just 4 million, right? 4 million, 4 and 2 times 10 to the power of 6. So 4 times 10 to the power of 6 divided by 4 is just 10 to the power of 6 plus k. So I have my a equals to 10 to the power of 6 plus k. Now next step, we use the other information here. X when time equals to 0 is equals to 2. And we use this information here when x when time equals to 2 is equals to 1000. So I substitute 1000 into the equation again. So 1/4 multiplied to 1000 square plus k equals to 10 to the power of 6 plus k, which is my a now, which we found earlier, that a equals 10 to the power of 6 plus k, to multiply to e minus time is 2 when when x equals to 1000. So I substitute 2 here, so e to the power of minus 1 is just 1 over e. So this becomes 10 to the power 6 plus k over e, and this part with 1 million divided by 4 is just 250,000 plus k. So when I multiply e onto here, so we have e equal to 250,000 e plus k, e equals to 10 to the power 6 plus k, and we are rearranging, okay, I'm moving this k over to the other side, becomes minus k, right? ek minus k. When I factorize out the k, it just becomes e minus 1 k, right? And then here 10 to the power of 6 comes from here. I'm just moving 250,000 e over to this side, okay? Then next I want to find what is my k, so I bring e to minus 1, divide e minus 1 on both sides, mix k the subject of the formula. I get 10 to the power 6 minus 250,000 e equal over e minus 1. So when I calculate, it's just this value, but the question wants to find the exact time, so I have to leave the constant in this exact value so that I can get the exact time. So, and this one a is just equals to, as we've seen, 10 to the power 6 plus k. So 10 to the power 6 plus 10 to the power 6 minus 250,000 e over e minus 1. So we'll see this on the next page. So again, it's still the same differential equation. You see 1 over 4x squared plus k equals to ae minus t over 2. We just substitute 1/4 x squared plus the a plus k. So k is 10 to the power 6 minus 250,000 e over e minus 1. So 10 to the power 6 minus 250,000 e over e minus 1. Okay, so a, right, here we have a equals to 10 to the power 6 plus k, so it's right in front of the e to the power minus t over 2. So e to the power minus t over 2, 10 to the power 6 plus the a, 10 to the power 6, this part is exactly the same as this part because this is just my k. So a equals to 10 to the power 6 plus k, right? And we have made sure that all this is correct. So I want to find, okay, what is the, this is the equation, so I want to find the exact values of k and a based on his claim. He said that you need 2 months to clear half the mines. So we have already found my a and k and a based on his claim. Now we want to find the exact time required to make zoo safe from landmines again. Safe from landmines meaning there are no landmines anymore, so we let x equals to 0. We want to find t when x equals to 0. So and x equals to 0, just substitute inside, so this 1/4 x squared will be gone, so we're left with 10 to the power 6 minus 250,000 e. But I decide to multiply e minus 1 over to the other side, so this would become multiply this to here, so 10 to the power of 6 e minus 10 to the power of 6, right, plus this e minus 1 will cancel away with this e minus 1, therefore I will just have 10 to the power of 6 minus 250,000 e and multiply to minus e minus t over 2. So 10 to the power of 6 minus 10 to the power of 6 really result in 0, so I have 10 to the power of 6 e. Well, I would like to wait a bit. So 10 to the power of 6 e minus 250,000 e. 10 to the power of 6 e minus 250,000 e. So because this I will just divide both sides by this term. So this term goes over, so it becomes the denominator here, and the numerator is still 10 to the power of 6 minus 250,000 e, then e to the power minus t over 2 on the other side. So next I will just ln log base e both sides, so I will have this ln, and this remains the same term inside of here, and after that I have minus t over 2. I multiply minus 2 on both sides, I get t. Alright, so this thing, right, so notice there's the e on both of these terms, so I take out, factorize out 1 over e, which is e to the power of minus 1, so the e here disappears. Right, left with the numerator is still the same, and this thing, so after that, because ln AB equals to ln A plus ln B, ln and A multiplied B is ln A plus ln B, so ln A ln E minus 1 is just minus 1 plus ln B, this term. Okay, so everything just check is still the same, so then minus 2 multiply to everything inside. I get minus 2 multiplied by minus 1 is 2 minus 2 ln this thing. Alright, and we realize that I can divide it by 4 zeros from top and bottom, so 10 to the power 6 becomes 10 to the power 2, and 25 times 10 to the power 4 becomes 25, and this one becomes 10 to the power 2, and the 4 zeros are cancelled away, so minus 25. So we have this term over here, and 2 minus 2 ln, I can ln A divided by B is just ln A minus ln B, and I couldn't simplify this further, and if I were to calculate this term, it should be about 3 point something month, which is a reasonable time frame according to clear the mine, given that it cleared half and is inversely proportional, you clear faster at the end, so it's about 3 months plus, right? So that's it for this tutorial.